here. I would probably distribute the r through now. Anybody have any questions on where I got that from? I'm going to dot this one, so when I distribute this r through, I get r root 1 minus r squared minus r squared dr d theta. And we should be able to integrate this pretty easily. This one right here, basic u sub. Let 1 minus r squared be u. The derivative of it's out there, kind of. This one, 1/3 r cubed. You're in business. So if you forget this, right, if you forget that r, not only would you be wrong, but the integration would change quite a bit, wouldn't it? 1 minus r squared, root 1 minus r squared, you would do that with a trig sub instead of a basic u sub. And so you'd be doing a lot of work for nothing. So dot, dot, dot. All right, we have one last type of thing we're going to look at in this section. And we're not going to get too heavy into it. I just want you to know it's there. The idea of a type 1 region in Cartesian said that we're going to stick our x's between two constants, and our y values will be stuck between two functions. So as your x changes, your y values may vary between two functions, right? That's type 1 Cartesian. If we do something similar in polar, what we're going to do is we're going to let our theta still be stuck between two constants, so between alpha and beta. So that doesn't change. But instead of saying that the radius has to be stuck between some small radius and big radius, I'm going to say that that radius is a function of theta. The inner radius is a function of theta, and the outer radius is a function of theta. And when you do that, you get a type 1. And what happened with the type 1 over here? What was the major thing that we had to be careful with? What was it? F1 of x and, no. Was it F1, G1? G1, G2, right? What was the major difference between this and like just a rectangle? That we're going to have, or limits of integration were going to be functions, which also forced our hand when it came to the order of integration. We had no choice. We could not switch the order of integration. Same thing's going to happen here. If you have something like this, your outer limit of integration is going to have to be your d theta, because that's going to be stuck between alpha and beta. Then you're going to have dr. Your radius is stuck between two functions of theta, h1 theta, h2 theta. And then this in here, it doesn't change. F of r cosine theta, r sine theta. So you see now, oh, what am I forgetting? R. R. So see, I can't switch these because these are no longer constants. I'm going to give you one example of this. And it's basically the problem that was going to be your problem 3 for your take-home, which I've changed, by the way, if you came in late. There should be a new copy of the exam on the desk. Problem 3 is changed. I like this problem. This is a really, really good problem. A sphere of radius 3, it's actually a solid. Imagine you have a solid ball, all right? And we're going to drill through the ball. And when we drill through the ball, it's going to take some of the material out, and this ball is going to have a new volume to it, right? So here it is. You can look through there, we see, right? So the idea here is that the radius of the sphere is 3. And I come in here with a drill bit that has a radius of 1. But this drill bit, I'm not going right through the center of the ball. That would be too easy to find the volume. Instead, what I'm doing is I'm drilling so that this is the x-axis, by the way, this is the y-axis. My drill bit's coming in here, and the center of the drill bit is here, and the drill bit always runs tangent to the z-axis. So here's my z-axis. My drill bit must always be touching that and going, basically it's going straight into the sphere, right? But it's offset. Do you see how it's offset? What is the volume of the remaining object? That's the question. It's a very difficult question to answer by hand, which is why I changed it. But we can set the integral up pretty easily. Any ideas on how you'd want to do this? Find the equations. You want to find the equations of the sphere and the cylinder? Or, okay, so what's the equation of the sphere? What was our radius? I think on this problem it's 3, right? On this one, I thought take home it was 4, right? Sphere radius 3. So 9, that's your sphere. All right. Cylinder, you want the equation of the cylinder? What is the equation of this cylinder? X squared plus y squared equals 1 would be a cylinder, but that would go through the origin, wouldn't it? Wouldn't that be right up through the center? I don't want it there. Where do I want the center of that thing to be? The center of it should be at 1, 0, shouldn't it? So look, if I'm looking straight down on this, let's say this is my x-axis, this is my y-axis. Here's the sphere, right? Radius 3. My drill bit comes in here like this. Right? Comes in like that, drills out. So the center of my cylinder should go through this point 1, 0. Very good. All you do, remember how we shift things around, right? X minus h squared plus y minus k squared. The h and the k move your center. So this is going to move it to 1, center to 1. Okay? Well, I've done what was requested. It was requested that we find the equations of each one. Now, find the what? The range. How do you mean range? You mean like the polar stuff, like r and theta and all that? I'm okay with that. But I would still like to hear, like, what's the method? Like, what are we going to do? Like, what are we finding the volume of? What do you want to find the volume of here? So you're trying to go about this problem by actually finding the volume of what we took out? Yes? Do you know the volume of the sphere if we never took anything out? Yes, right? Yep, go ahead.
It's something which is that you just find the volume of the cylinder and subtract it from the sphere.
I agree, kind of. Okay, yes, we all can find the volume of a sphere, right? There's no calculus involved in that. We just look up a formula for it and we're done, right? If we know the radius, we know the volume. So we take that answer and we subtract from it the volume of the cylinder, kind of. Because the problem is that, what's the problem?
The cylinder goes on.
Yeah, see, the cylinder keeps going up. So where do you cut it off? at the top, right? What's the top look like, though? Let me see. I thought I had done this where you could see it. Doesn't look like I did. Oh, here we go. That's what I wanted to do. If I take this all out, yeah, it's hard to see that. I'm going to try and zoom in on this. I hope this works. If I rotate this, yeah, that's going to work. You see, that top edge of the cylinder is part of the sphere, isn't it? You have to account for that. So let me go back and ask you a question. Do you have a top cap and a bottom cap? Yes? Right? The top cap of this part that we drill out is the sphere. What's the bottom cap? The sphere on the other side, right? Now I could make my problem a little easier by, instead of going on the sphere to the other side, I could just use the XY plane as the bottom and then find that volume and double it. You don't want to do that? I like that idea. Okay, so the top part's going to be the sphere. The bottom part's going to be the XY plane, which is z equals 0. And the only thing left is what's the region of integration. So let me kind of write what I've said down here. I'm going to go with the approach. My approach is going to be that we have a top function, f of xy, which is the sphere, but I have to solve it for z, don't I? Oh, we love seeing x squared minus y squared, don't we? And then the bottom function, which is going to close off the bottom of the solid, we all agreed would be 0, right? And now the region of integration. Isn't the region of integration that circle? The trouble we have right now is putting that into polar coordinates, because I'd love for this problem to be in polar coordinates. Is that a rectangular polar, is that a polar rectangle? Is your angle between two constants and your radius between two constants? So if I look at this angle, if I rotate, let's say to here, is my radius between two constants? Imagine dotted line right there. So I'm allowed to walk from here to here, right? If I rotate a little bit more to here, is that radius still the same? It's not, right? If I rotate this much, I'm allowed to walk out that far. But if I rotate further, I can't go as far, can I? And if I rotate even more, it's even shorter. Agreed? Somehow, how far I walk out is a function of how far I rotate. And this is what I was just getting at a second ago with that picture that we had, where I said we had h1 of theta, h2 of theta, right? Your angle's allowed to change, but how far you walk out changes when your angle changes. That tells me it is not a polar rectangle. So how in the hell do we get the restrictions that we need? We still need some restrictions on theta, and we need some restrictions on r in order for us to convert to polar, right? So we sit here and we look at it and we think about it, and then we realize, wait a minute, hold on. What do we know about that circle? What I know about that circle is that it follows this equation, right? That's the equation of that circle. In two-dimensional space, that's a circle. In three-dimensional, it's the cylinder. But do you agree? Now, I'm just going to mess with this for a second. I'm going to expand this out, right? Anybody see anything in there? Think polar. Think polar. x squared plus y squared is r squared minus 2, what's x in polar? R cosine theta. Got that? And then 1 and 1 on both sides, subtract 1, and you get equals 0. Now remember what we're trying to do. We're trying to find restrictions on r and theta. Theta should be stuck between two constants, but my radius should be stuck between two functions of theta. Can you solve this equation for r? It's a quadratic in r, isn't it? What can you factor out of each of these? R. So if I have to factor out an r, I get r, and then r minus 2 cosine theta equals 0. Set each one of these equal to 0. What do you get? R is 0, and r minus 2 cosine theta is 0, which means that r is equal to 2 cosine theta. So in order to draw this circle in polar coordinates, you need r to be 0 or r to be 2 cosine theta. Now think about r being 0. If r is 0, does that draw this circle? No, if the radius is 0, where are you? Right there, this point right here. Okay? That point is taken care of by that equation right there. Then this should draw the rest of the circle. Let's see if it does. Are y'all with me? Let's see. Let's let theta, just for example, let's let theta, I'm going to do a good old-fashioned t-table. Theta r. If theta is 0, what's cosine of 0? 1. 2 times 1? 2. So if my angle is 0, then I should walk out 2. So if my angle is 0, I should walk out 2 and draw a dot. If my angle is pi over 4, how far do I walk out? Well, cosine of pi over 4 is root 2 over 2 times 2. It's just root 2. Root 2 is about 1.414, something like that. So 1.414 is about this far, right? But I'm supposed to walk out that far when I'm aimed at pi over 4. Pi over 4 is 45 degrees. Wow, that's right there. Do y'all see that? What would happen, and this is kind of an absurd case, but what happens if my angle is pi over 2? So I'm aiming straight up and I'm saying, okay, how far do I walk out? Cosine of pi over 2 is 0, so it says don't go anywhere. So guess where you are? Right here. Got it? So far, I can draw the top half of this circle by letting my theta go between 0 and pi over 2. Understand? How do you think we're going to get the bottom half?
Negative.
Go negative. So if you go down and you start letting theta go negative values all the way to negative pi over 2, you'll draw the bottom half. So do y'all kind of get this? My restriction on theta is going to be between where and where? Negative pi over 2 and pi over 2. And then my restriction on r, how far I walk out, always has to be between 0 and 2 cosine theta. This is h1 of theta. This is h2 of theta. Now this is a true function of theta, isn't it? Theta actually makes a difference here. This one doesn't make a difference. 0. Questions? This is what we were looking for, right? This is what we were hoping for, is something that would draw this region, and I believe we've got it. All right, now double integral time. What we were going to do is we were going to find the volume of the part that was drilled out. And so we decided to take a look at the top cap being the sphere and the bottom being the xy plane and then doubling the answer, right? So the part that we're drilling out, and I'm going to make sure I'm clear on this, the volume of drilled out